Hey, welcome to Unit 4, Lesson 13. This is your lesson video. Today what we're talking about is solving systems of equations. So we're moving on from just solving them by looking at them to actually solving equations. This is one of my favorite things to do. I know, call me weird something, but I find it really satisfying to be able to solve a system of equations because I put a couple of lines on a graph and I get to actually look and see what those answers are. Come join me in this. So the first thing we're looking at, true or false. That's really what we're studying. For a long time, we solve an equation, we get x by itself, and then we verify that it's true. But here's the thing: now we have more than just x; we have x and y. And so what we're doing with this is we're going to use the lines to decide whether each statement is true or false, and we need to be able to explain our reasoning for both ways. We say the solution to 8 equals negative x plus 10 is 2. Well, let's look at this. What we're suggesting here is that x is 2. So when we talk about that solution, what we need to do is we need to substitute. So we see that 8 is equal to negative sign, but x is the only thing that's going to be replaced with the 2 plus 10. So what we would do is we would read this as saying 8 is equal to the opposite of positive 2 plus 10, which means that this is just simply 8 is equal to the opposite of positive 2, negative 2. And then we add the values together and we see that 8 is equal to 8. So this is a true statement. We know that it's true that x is equal to 2 because when I substitute my value for x, or my proposed suggested value for x is 2, when I substitute for x into the expression and I simplify both expressions, the expressions become equal to each other. So again, we're doing the exact same thing that we did earlier in previous lessons. We're verifying that a value is true. In this case, the next one, we are suggesting that x is equal to 8. And I guess I don't really want to box that in yet. That's something I kind of do. I usually don't throw the box on there until I've checked it and I know that it's really right. That's kind of a way of telling myself, yeah, hey, I've checked this and it's good. So now what I want to do is the exact same thing. I want to simplify. 2 is equal to 2 times the value of x now is 8. So substitute x and turn it into 8 plus 4. I want to simplify my expressions. 2 times 8 is 16, and I already know this is a train wreck because 2 is not equal to 20. This is a false statement. Since 2 is not equal to 20, then x can't be, right? So I can say this: since 2 is not equal to 20, then x is not equal to 8 because the equation is made false. Right? The first one, I could simply say since 8 equals 8, then x equals 2 is a solution because the equation is made true. That's the whole thing that we're after. We have to have true or false statements. So now when we look at the next one, we're saying that the solution here, x is equal to 8. You'll notice I didn't circle that on there. It's because it's false. The next one, we're saying x equals 8. Well, I'm going to go ahead and substitute. The opposite value of 8 plus 10 is equal to twice the value of 8 plus 4. And I'm checking to see, I'm verifying if this is really a true statement. Sometimes you'll see me put a question mark there because I'm questioning, is this really an equal statement with this expression equaling this expression? Negative 8 plus 10 is equal to negative 2. And 2 times 8 is equal to 16. And 16 plus 4 is equal to 20. This, again, is a false statement. Since this is a false statement, then we would say false, which means that a equals x or x equals 8 cannot be true. It just won't work because it makes this statement right here a false statement. So this would actually become an inequality. I look at the next one right here when I say x equals 2. That's my claim. Here's my evidence to decide if that's true or not. The opposite of 2 plus 10. And I'm checking to see, is this the same thing as 2 times 2 plus 4? The opposite of 2 plus 10 is 2, or is negative 2 plus 10, which equals 8. 2 times 2 is 4. 4 plus 4 is 8. Since 8 is equal to 8, since these two expressions are true, this is a true statement, then x equals -2 is an absolutely true statement. So when we go to explain these, we have to explain the fact that I can verify my claim as being true or false. So a little bit of a good review with that to double check. We want to look at this one right here. There are no values of x and y that make these two equations true at the same time. Well, what we want to look at, there's a couple of things. First off, I hope you remember way back when we looked at the values of the variables, and we said, well, if the variable terms are equal, then we either have no solution or all solutions. If they're not equal, then we have one solution. So when we look at these, this says that there's no value. So they're suggesting that there is no solution that makes these two equations true at the same time. Well, we actually can do a little bit of a comparison. You see how both these equations equal y? What we see is that this -x plus 10 is equal to y. Okay, but at the same time, we also know that y is equal to 2 times x plus 4. So in reality, the expression here on the right is equal to the expression here on the left by virtue of equaling the exact same thing. So we can actually say -x, or the opposite of x plus 10, is equal to 2 times x plus 4. And then I can use my properties of equality to finish this off to verify that. I can add x to both sides to give me 3 times x plus 4 is equal to 10. I could subtract 4 from both sides, and I get 6 is equal to 3 times x, and x equals 2. That's awesome. But then what about y? Well, to be able to figure out y, this is where I need to go in there and I need to substitute that value in here for x. So what I do with this is I would say y is equal to 2 times 2 plus 4, and y is equal to 4 plus 4, or just that y is equal to 8. Okay, that's one of them. The other equation said that y is equal to the opposite of 2 plus 10, and what we see is that is -2 plus 10, or y is equal to 8. And I want you to notice something here. Both values of y come up the same, so that means that when x equals 2 and y equals 8, there is an ordered pair that's created here that says that my actual solution with this is going to be, got a little wild right there, is going to actually be 2 and 8. And what I want you to see with this is go back. You see this graph right here? These are those two equations that we just verified, and they cross each other at 2 and 8. And so what we've done is we've taken a long route to proving that 2, 8, that ordered pair, is the one solution that makes both equations true at the exact same time, such as right here. This says there's no values. That is absolutely false, and we've proven that using substitution. Okay? Our goal today is that we're actually solving equations using substitution, and we've actually been doing this for a long time. We just didn't really know it yet. So when we're looking at these and we're talking about how we can know when we're using substitution, we've actually used substitution to talk about these graphs for a long time. So what can we do? Here's 3 systems of equations that are graphed on a coordinate plane, and we need to match each of the figures on the equation, or match each of these figures to each of these systems of equations. So our questions would be, which one is going to match where? We can do a couple of things to be able to look at this. First off, number 5, y-intercept of 5. Looking at this piece, this has a y-intercept of 5 and a y-intercept of 20. That's definitely A, because I see both those as y-intercepts. B, -10 and -1. Nope, those are not those y-intercepts. But this one right here, I see that this one goes through -10 for sure. This one's super close to 0. I think we can go ahead and assume that. This one right here, passing through between 10 and 15, yeah, that's probably 12. And then up here above 25, that's probably 27. Sometimes graphing or matching these systems of equations to the graph is a super simple process, such as understanding the slope and the y-intercept. In this case, I just did the y-intercepts to be able to match up the graphs to the systems that are given. What I can also do, though, is I can do this. I can say, since both of these are equal to y, I can say that the expression 3 times x plus 5 and the expression negative 2 times x plus 20 must be equal to each other because they both have the exact same outcome. And then from there, I can go ahead and just simply solve for x plus 2x here. So eliminated there. I'm going to eliminate the 5 here because I don't have a lot of space. And I get 5x is equal to 15, which means x equals 3. As I look at each of these, what I know right now is that my system of equations right here, my x coordinate is equal to 3. I can find my y coordinate by simply substituting right here, and I'll know if I have the right ordered pairs if I can substitute x for 3 here, x for 3 here, and then my y comes out exactly the same. 3 times 3 is 9, and 9 plus 5 is 14. So I get 14 in the top when x is equal to 3. In the bottom, negative 2 times 3 plus 20 is negative 6, and negative 6 plus 20 is 14. And I know now that my solution to these two equations is 3 and 14 because when I substitute the x and the y, it makes both expressions equal to each other. I can take that ordered pair and I can simply say, where do those two lines intersect? This is the only spot that's reasonable to 3 and 14. So we've verified that A is really matched up with this one down here with A. Can do the same thing again right here. 2 times x minus 10 and 4 times x minus 1 are equal because they both equal y. I can subtract my 2x, subtract my 2x, and then I can add the 1 to eliminate here and the 1 to here, and I get 9 is equal to 2 times x divided by 2, and x, excuse me, negative 9 is equal to negative 4 and 5/10. Excuse me. And simply based on that piece, now I can look at these other graphs. This one, the intersection right here, the x is going to be more like negative 11, negative 12. Whereas this one, the x is more reasonable to believe that it's negative 4.5. And then I can solve for y by substituting that x. Sorry about that. I think I'm good now. I can do the same thing with c, but for the sake of time and my voice, that I clearly need to move on to the next one. When we find a solution to each system, we need to be able to check that solution is correct based on the reasonableness of, we need to find that solution to each system and check that your solution is reasonable based on the graph. And that's exactly what we're doing here. Checking that our solution that we came up with, we found the solution, and then we checked the reasonableness of it by finding it and comparing it to the graph to make sure that it really does match up where it looks like it was or where it would appear to be. And that's one of the great ways that we can do this, is we can solve using what we call substitution, and we can verify using substitution. So substitution is a very critical piece with this. I'm going to 3. I actually won't see you to be able to give you the pages that they're suggesting, but I will talk to you about a couple of these pieces. Graph each system of equations carefully on the provided coordinate plane. You can go ahead and do this in the interactive piece of it, but what I want to just get a quick recap is this. Describe what the graph of the system looks like when it has one solution. So one solution, the lines intersect. And the reason they intersect is because they have different slopes. Now, if you remember back to previous lessons when we talked about solutions to linear equations, we saw that we had equations that had something like this. 3x plus 2 is equal to 2x plus 1. What we can look at with this is we've seen that this is really a comparison of two expressions, and we saw that these variable terms were different. Well, this would be no different than looking at the equation and saying y is equal to 3x plus 2 and y is equal to 2x plus 1. And what we can see right here is that we see different slopes, 3 and 2, but we also see that the variable terms are different. So the variable terms are actually the slope. So the variable terms are not equal, meaning slopes are not equal. So slopes, variable terms, not equal, that means one solution. Zero solutions, we're talking about parallel lines, different slopes. So the slopes are not equal. Excuse me, yeah, they are. They can't be parallel unless they're equal. So equal slopes, and then different y-intercepts. So again, we go back to this thing about the constants and the variables. So variable terms are equal when we're talking about x. And then different y-intercepts, we're talking about constants are not equal. Infinitely many solutions are really just one line. Those lines, they do what they call coincide, where they overlap. And the reason they do this is because we have equal slopes and equal y-intercepts, which means that we have variable terms are equal and then the constant terms are equal. Please, please, please remember this is so much like what we did in the previous lessons of talking about solutions to the equations. So we really don't need those pieces. We really need those pieces from the past to be able to help us with this stuff in the present. Sometimes it's really much easier to solve a system of equations without having to graph the system or graph the equation itself and look for an intersecting point. In general, whenever we're going to solve a system that's written like this as y is equal to some stuff and y is equal to some other stuff, we know that we're looking for a pair of x and y values that actually make both equations true. Specifically, we're looking for what values of y will be the same in both equations. That means that this some stuff and some other stuff is equal. So what we're really saying is that y is equal to y, but we know that y represents this and y represents this at the same time. So that some stuff and some other stuff, they're going to look the same. So when we look at this example, y equals here's some stuff and here's some other stuff, meaning that some stuff can be equal to some other stuff. I really get a kick out of this, or how the authors wrote this. Makes a lot of fun for me. We can solve this equation by substitution. So this some stuff and some other stuff, this is substitution. I've taken some stuff and turned it into 2 times x plus 6. And I've taken some other stuff and turned it into negative 3 times x minus 4. And now what I'm doing is I'm solving everything in here for x. I'm following those properties of equality, addition property of equality, to get the 3x to this other side, and then the subtraction property of equality to get 6 out of there, and then the division property of equality to get x all by itself. And once I have x, I'm still left with another variable. I have to find y. It's only half of the values that we're looking for. So I have to find the y, and what I can do with this is I say y is equal to 2 times negative 2 plus 6, because I thought that the solution is negative 2 for x. And then negative 2 for x in the other equation gives me y equals negative 3 times negative 2 minus 4. And then when I simplify, now I forgot they don't show it on there. When I simplify, take a look what I see. Y is equal to negative 4 plus 6, which makes this y is equal to 2. And on this one, I have 6 minus 4, which means y is equal to 2. And then look at that. They both come up to the same. So what does that mean? That means that we're suggesting that when x equals negative 2, y equals positive 2. And when we see the graph of these two lines, they should cross each other or intersect each other right there at negative 2 and positive 2. And when we see the graphs in both cases, they intersect at the exact same point, which means this is one solution. And that one solution that goes with the system, y equals 2x plus 6, and y equals negative 3x plus 4. Whoops, sorry, minus 4. Make sure I got those right. Yep. As a system, that one solution is going to be negative 2, positive 2, where we have the x coordinate and the y coordinate proven in both of them. So no solutions, in this case, the lines, so when we talk about no solution, never intersect. This would be parallel lines. Okay, and what we would see with this is we would see same variable terms. Actually, we're going to change this a little bit because those variable terms actually mean the same slope. We would see the exact same slope, but a different y-intercept. Meaning that it'd be the same coefficient of x, but a different constant. Exactly one solution would be this, just simply different slopes or different variable terms. And then infinite number of solutions. I'm sorry we didn't see infinite number of solutions and no solutions yet. Infinite number of solutions are actually this. They are the same line. They have the same slope, same y-intercept, meaning they're the exact same lines. So we're going to see this just a little bit as we get going with more of these lessons. But for right now, here's the spot where we need to break through. We need to understand that the key to all this is substitution. That's our critical and our primary method for this. We are substituting those values to be able to make sense of our equations, to solve for x, to solve for y, to verify for x, to verify for y, that we really have the right solutions here. So thanks for taking some time. Check in if you have some questions, and have a great day.